Hi, everyone. Thanks for hanging in there. We're almost to the wine and cheese. So I am going to continue our session's theme and talking about transiting exomoons, and even more specifically on how we use JWST to search for transiting exomoons around the free-floating planetary mass object YZO855. I'm a fourth-year PhD candidate at UC Santa Cruz, but I do work very closely with Marianne Limbach, who's at University of Michigan. And I have the opportunity to work with a lot of the folks listed here, including Andrew Vanderberg, who started off our session. So in many ways, this talk will be complementary to a lot of what he introduced to us. And because the previous two speakers did a great job at setting the stage, I won't talk too much about background motivations, but I do think it's worth taking some time to re-emphasize a few things and to orient us within the exomoon field, especially since there are just so many different paths that people are exploring to try to push us closer to that first confirmed detection. So here I've listed just a couple of candidates. First, what's probably the most well-known exomoon candidate, and then also a very recent one that I saw pop up on the archive within the last week or two. And what's interesting to me is the diversity of these candidates, especially in comparison to what we see within our own solar system. So earlier this year, I attended a conference, and it was about circumplanetary disks and satellite formation. And there was a good amount of exomoon people there, a good amount being 5. And everyone was talking about approaching this problem in a different way. And each talk included some version of this is what I mean when I say exomoon. And I think that that's a really good representation of where the field is at the moment. And so it's kind of in these relatively early stages. And so it kind of shows us how unique these methods can be in terms of the sorts of systems that we're able to probe and the types of satellites that we are sensitive to. So, for example, in the case of the Tichy and Kipping analysis, the signal here corresponded to a very large exomoon. And then in this recent Cross study, they used high precision astrometry to find a very massive moon that was about half a Jupiter mass, a little less. But regardless of which path we're taking in all these different methods, at the end of the day, what we want to do is try and bridge this gap. So on one end, we really want to extend our understandings of solar system moons out into the rest of the universe. And of course, we've gotten the opportunity to learn about some of our neighbors in great detail. Victoria just told us that these can be some of the most interesting sites in the astrobiological context when we're looking for life elsewhere. And of course, that translates really nicely to the exoplanet motivations as well. So on this end, we've passed the 6,000 mark for the number of confirmed exoplanets, which is very exciting. And the field is seeing this really gradual shift from just detection to now characterization and even searches for these very specific sorts of systems. And so we're really at this point where we have a sample, albeit very small, of moons that we do know a great deal about in combination with the different exoplanet techniques and now JWST that puts us in a really great position to hopefully finally bridge this gap that's left by exomoons and exosatellites observationally. So as Andrew previously introduced, the approach that we take is to search for the signal that's caused by the moon in the planet's light curve. So directly for the moon's transit in the planet's light curve, which is a little bit different than if you think about TTVs or TTDs, for example. And so the challenges with this method, of course, being that a bright host star that's nearby could easily drown out an exomoon signal like that. Also, the nature of the transit method is going to require very specific geometry. You have to be edge-on or close to edge-on so that the moons will actually transit in front of the planet. And finally, probably one of the most difficult things is the host variability itself. So as the video showed, we get these really complex light curves that could be due to the presence of clouds, spots, for example, disequilibrium chemistry. And so to describe kind of more in detail how we address some of these challenges, I'm going to walk us through a case study where we use this method to search for moons around YZO855.
So YZF5 is a planetary mass object. It's somewhere between 3 and 10 Jupiter masses, which puts it below that deuterium burning limit of 13 Jupiter masses that we typically define as a start to the brown dwarf regime. And since it's free floating, that means that we don't have to worry about a host star, like we mentioned previously in the challenges. And so that allows us to focus on the planet's light curve. It's also 250 Kelvin. So as Andrew mentioned, the types of objects that we are typically going to want to look at are these really young, bright ones that are still bright from the heat of formation. But we can look at YZF5 because it's really nearby. So even though it's faint, this still works for us. And we have 11 hours of time series spectroscopy with NIRSpec on JWST. So we took a spectrum every 15 minutes. So we have 44 of these really high quality spectra. And just for reference, I like to show the previous spectrum of YZF55. So this was taken with Gemini compared to that same wavelength range with JWST. So you just see we have so much more detail here. And as a note, I do want to mention that these observations were originally optimized to search for water clouds on YZF55. So weather was kind of the primary science case here. Okay, so with this method, something that we're going to use to our advantage is the fact that the light curve is spectrally resolved. And so what we assume is that if you have a dip that's caused by a moon, that would not be wavelength dependent because it is physically blocking out some light. So it's the total amount of light decreasing. But that's not necessarily the case for these other things varying like clouds. And so they could be absorbing at very particular wavelengths. And so this is kind of the full range of our data shown in this 2D format. So we have a spectrum at each time, and you can imagine every row here being a spectrum. And so what we're going to do is we're going to pull out two light curves from wavelength regions that have different variability patterns. And so if there's a transiting moon, then it should cause a dip in both versions of that light curve at the same point in time. So here, region 1 is characterized by this sort of dark, bright pattern. And then region 2 is dark, bright. Okay, so these are the light curves that we get from those two regions. And so using this idea of wavelength independence, what we do is we fit our data with two different models. One is a GP plus transit model. So we're saying there's some shape to the host variability. And then on top of that, there's also the exomoon transit. And so it's going to be a concurrent dip in both of those light curves. And then our GP only version says this is just what the host planet's variability looks like. It does not assume a transit. And so we have our two models, and what's spit out at the end is this log z value. And you can just think of this as how confident that we are in the model. And the model with the bigger log z is going to be the model that is favored. So the difference between them is the delta log z, and that tells you how much it's favored. So it kind of corresponds to this table here. And so I want to go back to this concern about host variability. Jackie asked a question earlier, and the question is, there's a lot of bumps and wiggles in the light curve. How can we distinguish those from real transits versus just natural dips that are mimicking them? And so we approach this by assuming that the variability is symmetric about some average. So maybe there's as many brightening events as there are dimming. And so if you flip your light curve, then you can expect that the host variability shape should remain relatively the same. But now that it's flipped, there's a guarantee that there are no real transits in that light curve. And so if you run the models on the original light curve and then the flipped, you kind of start to get an idea of this. So these are the numbers that we're working with. You don't have to pay attention to the specific values. I'll walk us through what's important. So as I said, a model with a larger log z is going to be the model that's favored. So for the original light curve here, this is saying that our transit model is favored over the GP only because the log z value is greater, which sounds great. But then we look at our flipped light curve and we see the transit model is also favored in this case, but we know that there aren't any real transits there. So in other words, this flipped light curve's delta log z is really serving as a correction factor for us. So rather than a final delta log z of 11.46, we really have to subtract off this correction factor. So that means that our final delta log z is actually close to 0. So there is not evidence for a moon in these observations. But we can ask ourselves if that's really that surprising, and it's not. So if we think about the probability that we would have observed a moon here, that's shown in this figure. So this figure is taking into account two different things. The first, that we don't know the inclination of YZ855. So maybe there are moons that are going around it, but maybe they're going this way and they never were going to transit. And then also the fact that we have an 11-hour observation. So maybe the moons would have transited, but we observed while they were going over here instead of passing in front. And so this is the probability shown here for the different mass and radius estimates for YZ855 with the Galilean moons shown for reference. And so if we think about a moon around YZ855 at an Io-like separation, so the purple dot here, if YZ855 was the largest and most massive instance of itself, then we would have had a 15% chance of catching an Io as it was transiting. And then if YZ855 is the smallest or least massive version of itself, then that goes down to about 6 or 7%. So it's actually not that crazy that we didn't find a moon, but this is just for one object. And so of course, these chances are only going to continue to improve as we observe more and more. So in theory, say we conduct these observations again and again under similar conditions. So again, that 11-hour observation and without knowing the inclination. If there's Galilean systems around these objects, then after 18 observations, you should have a 95% chance of catching a moon as it's transiting. And of course, that probability is only going to increase if you were to continue observing it for longer, or if you know that a free-floating planet is oriented in a certain way, maybe it's close to edge on. So the caveat here is that just because we have some data that has a transit in it, that doesn't guarantee that our models are going to see it. And so we have to figure out how well our models are doing in recovering these transits. So although we didn't find the moon, the next step is to test that model performance by injecting artificial transits and retrieving them. And so I did this, 50 tests each for 6 different transit depths, ranging from 1% down to 0.1%. And I just want to show an example case here. So this is an injected 50-minute transit at about 4.2 hours, and it's a depth of 0.3. And so we see that the models do a fairly good job at identifying the host variability. And when we subtract it off, we see our transit is left there. But of course, in a blind transit search, we're not going to know where that transit was to begin with. So we do have to go back to this idea of the log z's. And so for this example specifically, it comes up to a decisive confidence that the GP plus transit model is favored here. So this is a sort of visual for the model performance. So these plots are showing the injection time on the X and the retrieve time on the Y. So ideally, we'd want these points to be falling along the diagonal. And I think I'll actually skip to this next plot that's showing the summary of that. So this is the final summary plot showing the fraction detected. So we consider a detection to be if the retrieve time is within 15 minutes of where it was injected. And so you can kind of see the shape of this fall off as we move to smaller and smaller transits. But we can ask ourselves what these results really mean. So although YZ855 is close to Jupiter mass, it's expected to be 3 to 10 times more massive. So by only focusing on size analogs, we might overlook the significant influence that the predicted mass of YZ855 should have. So satellite formation theory tells us moons should be common, and especially that the total mass ratio should be about 10 to the negative 4 for the mass that you would expect around a planet. And so what I did is I scaled up these Titan and Io masses to find their corresponding radius values, and these are the ranges we get. So these are Titan mass analogs and Io mass analogs. And so you see we're sensitive to these Titan ones and to some Io mass analogs. Okay, so we kind of had to combine both of these ideas. First, the probability that the moon would be transiting to begin with, and then how well our models do at recovering those transits. And so combining these ideas, we get that you'd have a 91% chance of detecting a Titan mass analog if you were to observe 18 WISO-855-like objects. So when I say WISO-855-like, that just means similar to the observations that we just did, unknown inclination, and also 11-hour observations. And this was all described in a paper that was just published in the last month in AJ. So in the future, of course, what we want to do is to continue searching similar data sets. So Andrew talked to us about the ONC observations, but also if we continue to look at very specific objects, the next one that I am going to be doing is VHS 1256b from Niall Whiteford's data set. And I will say when we do this, it's not necessarily an exact replica of what we've done previously, especially because each of these objects are unique in their own ways. So they're going to give us different insights into the problems because of that. And just continuing to refine our methods, if we figure out which observational setups are going to be the best, which different sort of approaches in the data analysis, and even other fun things like if exomoon features themselves might influence transit shapes. So if you have an atmosphere or rings around a moon, what would that look like? So I will leave this up and take any questions. Thank you.
So the I'm trying to understand how your models distinguish between a transit and variability, right? It seems kind of magical. So is the Gaussian process is essentially keying on the time scale of the correlation of the brightness variations being longer than the duration of a transit? Is that essentially what's going on?
Yeah, so that's part of it. Yeah. I will say, so whenever it's saying that there's a transit there, it's saying there's something that looks like a transit there. So for example, in the case where we searched for this, not with any injections, it did recover a transit. And so that's saying the GP plus transit model is a little bit favored. But when you go back and look at it, what it's doing is it's kind of latching on to the lower part of, I can go to the figure here. But what it's doing is it's kind of, does have a pointer maybe? Oh yeah, okay. It's latching onto this feature right here. And so I will say it does take into account kind of the shape of the variability in general, but also we don't necessarily know like the full rotation period of WISO-855. And so kind of going back and looking at what it's actually picking up and relying more on the higher delta log Z values that are more confident is going to be what helps.
Very nice talk. You talk about WISE 0855 like objects, and WISE 0855 is really unique. Would there be any, for example, brighter sources that you could make a larger sample and maybe do this from the ground and not need a lot of JWST data to test this out?
Yeah, so the ONC project that Andrew talked about a little bit, that's led by Marian Limbach. So that's going to focus on looking at 50 free-floating planets, or I shouldn't say free-floating planets because some of them are above planetary mass, but of 50 kind of rogue world. And so those are younger, brighter, that could be from the heat of formation still. And so it does, lend itself to a little bit, maybe more of an easier analysis. But at the same time, the same kind of issues are still going to be popping up in terms of variability and stuff like that.
What about like T dwarfs instead of Y dwarfs?
There are, I believe, some T dwarfs in the sample too. So yeah, I think the question too is whether the moons or satellites around them are going to look the same. And I think we don't necessarily know the answer to that yet.
Okay, thank you.
We have time for one more quick question.
Thank you. This is very quick. What was the motivation or the reason for choosing that specific?
Yeah, that's a great question. So the idea was just that we could do this. Yeah, the original motivations for this data set in particular was to look at the weather. And so exomoons was kind of an additional science case that Marianne, mentioned in a paper. And so, yeah.
So this is just a comment that the general predictions of theoretical studies of free floating planets and migrating planets and all that is that because of the ejection, because of migration and all that stuff, the disk around the circumplanetary disk, and if there was any satellite, they got ejected. They don't. So I genuinely hope, as a theorist who does this type of thing, I genuinely hope you can prove me wrong, because that opens a lot of good doors for us to explore our theories and improve them. So good luck. I really hope that you can do this.
Thank you.
Let's thank Mikayla again.